All right. Hello, class. Thank you for tuning in and watching. Um, I'm here with 4 more pages from the workbook. So we're going to be doing forces. Hello, brother and sister. That's kind of cool, brother and sister both watching together. Hey, Theo. Hey, Sydney. Hey, Vicky. Thank you for watching. I appreciate it. Good job staying focused during the quarantine. So I've got 4 pages from the workbook for you. This is going to be on forces. And then tomorrow we're going to talk about circular motion and gravity. And then Friday we're going to start talking about energy. Hey Ray, hey Izzy. All right. So let's get into the physics. Let's get it done. So I'm going to be doing pages 39 through 43 in the workbook today. So we've got a scenario. It says a bulldozer of mass M pushes a cube of cement of mass little m across rough ground. Bulldozer and the cube are speeding up. Okay. So that means that there's a net force that is positive, all right, because they're speeding up. The dots below represent the bulldozer, the cube, and the bulldozer cube system. Draw free-body diagrams showing and labeling forces exerted on each system. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. For the bulldozer cube system, draw an external force diagram. So I'm going to assume that the bulldozer is heavier than the cube, okay? All right, so if we look at the bulldozer has a downward weight force like this, okay? And then the cube has a downward weight force as well. I'm assuming that the cube is less massive than the bulldozer. The total weight force on the bulldozer cube system would be the sum of these two, which is going to be a longer arrow going down. Now you would want to label these arrows. I'm not labeling the arrows because it's a little bit clunky for me to do that. Now we're going to have normal forces as well. The bulldozer isn't accelerating upwards, so the upward force has to match the downward force, so that you would want to have your normal force being the same size. Something like that. And here you have normal force being the same size. Okay, so what is propelling the bulldozer forward? Well, basically it's the ground. It's traction with the ground. So you would have an arrow going to the right, and this would be labeled as traction or some sort of a force from the ground. And then what is slowing the bulldozer down is a normal force from the cube that's in front of it pushing it backwards. So we're going to have a reaction force, which is going to be, I don't know why it's not letting me draw it, which is going to be this way. and that's the force from the cement cube. Notice how I'm drawing the force from the cement cube is smaller than the force from traction because they're speeding up. Now, if we look at the forces on the cube is going to have the force from the bulldozer. Now, you want to be very careful to draw the force from the bulldozer to be the same size. The force from the bulldozer on the cube to be the same size as the force of the cube on the bulldozer. That's Newton's third law. And then the cube is also going to have some kind of frictional force that is that's preventing it from going back. Okay. And it also has to be smaller. Okay. Like that. Because the cube is also accelerating. Now, what are the forces? So notice how if we look at the external horizontal forces, the internal forces cancel each other out, and all we have are the external forces. So this would be traction, and this is traction from the bulldozer, and then the other force would be friction on the cube. Okay. In the blanks above, write an equation stating second law in the horizontal direction for the bulldozer, the cube, and the bulldozer cube system. So I'm going to say that we have traction minus the force from the cube equals MA. All right? That would be the horizontal forces for the bulldozer. Okay. And then if we look at the cube, we have the force from the bulldozer minus the friction equals little ma. So two things I want to note here is that the cube has a smaller mass than or it has a different mass. So notice how I have the different letter. The accelerations, however, are the same because they're in contact with each other. So I use the same A. And also keep in mind that the force from the bulldozer is going to be the same as the force from the cube because those are action and reaction. If we add those two equations together, the total system has a mass of little m plus big M. Okay. And then the net force is going to be traction minus friction. Okay. So that came from adding the two original equations together. Use the equation created for the external forces on the bulldozer cube system to determine the acceleration of the bulldozer cube system. If the mass of the bulldozer is 1,000, the mass of the rock is 500. The force of friction on the bulldozer is 500. The force of friction on the cube is 2,000. So the force of friction on the bulldozer is I think, what I was calling traction. Okay. I would have called it traction, but so what that says is that traction minus friction is 5,000 minus 2,000, and then the total mass would be 1,000 plus 500 times A, and so that gives A equals 2 meters per second squared. All right, next scenario. A 300, let me check for questions. Sydney, you're also related to Sebastian and Elena. I didn't know that. So we've got a 300 kilogram box resting on a platform attached to a forklift. Starting from rest at time equals 0 seconds, the box is lowered downward with an acceleration of 1.5 meters per second squared. The dot below right represents the box. Draw a Freebody diagram showing and labeling the forces exerted on the block, or the box. Okay, so we're going to have normal force going up. That's the normal force from the forks of the forklift. And then we're going to have weight force going down. Notice how the weight force arrow is longer than the normal force. Okay? There's more downward force than upward force because it's accelerating downward. Okay? In a brief sentence, support the magnitude of the normal force in comparison to the gravitational force on the box. So basically, we must have normal force is less than weight force so that the net force is down, which results in a down acceleration. So saying something to that effect. Blake derives an equation for the height of the box as a function of time. Makes a mistake and comes up with y equals 9.8t. Man, Blake's a loser. Without deriving the correct equation, how can you tell that this equation is not plausible? So I would say y is a linear okay, I would say Blake has y as a linear function of time, which means the velocity is constant. This is not consistent with acceleration because it says that it's accelerating. At time t equals 0, the forklift also begins to move forward with an acceleration of 2 meters per second squared while lowering the box as described above. The box does not slip or tip while the forklift is accelerating. Draw a Freebody diagram showing and labeling the forces exerted on the block. So we can see here it looks like the box is not in contact with the vertical part of the forklift, like right here. You guys see that? So the thing that would accelerate the box forward would be friction from the forks. There's got to be friction from the forks that accelerates it forward. So we're going to draw pretty much the exact same Freebody diagram. We've got normal force going up. We got weight force going down. Okay, but then we've also got friction going to the right. Notice how I have to change this a little bit. Notice how, what's the net force going to be in this first diagram? We can see that the arrow goes up 3 blocks and down 5 blocks. So the total length is going to be 2 blocks. Okay? I'm going to draw my rightward force as being more than 2 blocks long. Why is that? Because notice how the rightward acceleration is 2 meters per second squared, which is greater than 1.5 meters per second squared. So that means that the horizontal net force has to be bigger than the vertical net force. Okay? In fact, technically I should have drawn it 30% longer because it's, 1.5 to 2 is a 33% increase. Explain in a brief sentence why the force of friction points in the direction you sketched in part D. I would say that I would say something like friction, the box accelerates rightward. So there must be a net rightward horizontal force on the box. Friction is the only force that could do that. Something like that. Quantitative analysis. When the box is only being accelerated forward, A max has one value. A max is the maximum acceleration the forklift can have before the box begins to slide. When the box is both accelerating forward and down, the acceleration is less. Explain in a clear, coherent paragraph length response why this is true. I like that question. Very good. Pay attention to this one because I think this is a good question. So what I would say, we know that the maximum value for static friction is equal to mu static times normal force. Okay? If the block, by the way, when it says a coherent paragraph length response, you can include equations if you want. Equations are the language of physics. So I would include an equation. For me, an equation is much more clear than writing a paragraph most of the time. Okay, so if the box is not accelerating downward, if the box is not accelerating downward, then normal force is equal to mg. Okay? If the box is accelerating downward, we just showed that the normal force is actually less than mg. Okay? This shows that the maximum friction force, or I should say the maximum static friction force, is less when the box accelerates down. This means there can be less horizontal acceleration. I think that's pretty clear. I'm going to leave it at that. All right, so I think I got one more question here. Let me see if I have any questions from you guys. Nothing. All right, Angela and Carlos are asked to determine the relationship between normal force on a box of mass m and the angle of incline of the box, theta, as the box sits at rest on the incline. The dot at right represents the block on the incline. Draw a free body diagram showing and labeling the forces exerted on the block. Okay, so we've got normal force, which points perpendicular to the block. We've got weight force, which points downward. Okay. And then we've got static friction, which points along this way, like so. Whoop. Like that. So those are the forces. Start with Newton's second law to derive an equation that relates the normal force with the angle of the incline. For each line of the derivation, explain in words what you did mathematically. Okay, so I'm going to choose. Now, what we did in these kinds of problems is we chose the y direction to be perpendicular to the incline. Okay, so that's the y direction. Okay. So keep that in mind. That makes this a lot easier. So what that means is that the net force in the y direction is going to be equal to 0. And I would say that because the box does not jump off the incline. A sub y equals 0. Okay. Now, what are the forces in the y direction? We've got normal force, and then we have this part, just that part of the weight force triangle. So if we look at the weight force triangle, here's the weight force triangle. The weight force triangle, only the y part of that. Okay, so we've got normal force and the y component of the weight. So my net force in the y direction is going to be is it giving me any, oh, it's not even giving me any more space. So I would say we have normal force minus the y component of the weight force equals 0. And then the y component of the weight force is going to be mg sine theta. So that means that the normal force is equal to mg sine. All right, I'm not going to explain it. I just explained it in words. Angela and Carlos then performed an experiment to test the equation they derived in part B. The following data are collected. Based on the equation you created in part B, what data should be plotted to create a linearized graph for this experiment? So basically we have normal force equals mg sine theta. Or what did I say? I totally goofed here. I'm sorry, you guys. The vertical part, this should have been mg cosine. Kudos to you if you caught that. I would tell the class, I would say raise your hand if you caught that, but I'll say comment in the live chat if you caught that it should have been cosine. Jin K asks, will we have an equation sheet for the AP exam? as far as I know, the AP exam is open notes, open book. So I think you can have an equation. You can use whatever information you want because it's going to be taken at home. But so I would print out the AP equation sheet. All right, that's an important point for everyone. Actually, you can use whatever information you want. Okay, so this should be mg cosine. So we can see that if I let y squiggle equal normal force, and I let x squiggle equal cosine of theta, then that would be an equation of the form y squiggle equals mg times x squiggle. And so that's the graph of a line. And furthermore, it would tell me that the slope is going to be mg. So that I answered part D as well. All right, and that's it. So that is my lesson for today. Thank you very much for those of you who tuned in. I feel like I had something I wanted to say. I can't remember what it was now. But just take it easy, and I'll talk to you again tomorrow. Miss you guys. Bye.